Okay, exercise 1.7, every non-empty X a subset of N has an in-min element. Now, this is the first one where I think things get really hard. This one stumped me for a long time. So, I'm going to start off this first video just doing it the wrong way. Not totally wrong, but basically giving you sort of my thought process and how I kind of stumbled, and then, I eventually came to a valid proof, but that'll be in the next video, so if you're not interested in my initial wrong or slightly wrong method of proof, then you can go ahead and skip this video. But if you like to know kind of where it comes from and have some sense of, how I thought about this, then that's what this video is all about. So, alright, to build some intuition for exactly what this is saying, suppose that X, this non-empty subset of N, does not have an in-min element. Well, then it must not have the empty set, because the empty set, it is easy to show, is in-min in any set where you find it. So the empty set must not be an X. Now, also, the number 1, which you recall is the set of the empty set, cannot be in-min, granted that the empty set isn't there, the number 1 would be in min if the empty set isn't in there, so 1 can't be in X, if, again, under the assumption for contradiction that X has no in-min element. Okay, and you can proceed likewise, right? Again, on the assumption that X has no in-min element, and it also does not have 0, and it does not have 1, it cannot have 2, and so on. Now, if we eliminate all of these elements from X, and X is a subset of N where N is just made up of these kinds of things, then we must be basically eliminating every possibility for what could be an X that would, I guess you could say that forces X to be empty, but we are assuming that X is not empty. Okay, so you can see where this contradiction should be coming from if we were to assume that X has no in-min element. Now, a comment on proof by induction, it does seem sort of natural and attractive to try to show that that X, has, must have an in-min by induction somehow. But although that seems attractive and might even work, I'm just a little suspicious of using a proof by induction, and here's why. Proofs by induction are generally a proof that every element of a certain kind of set has some certain property. So if you take, for example, the set of all n that are the result of adding the first I elements out of the positive natural numbers, if we argue that every one of these numbers satisfies this formula that we famously know they do, the proof by induction is successful just because we know that there is some onto function mapping from the natural numbers onto this set, so we can run through all of those natural numbers, showing that since it holds for each I, then therefore it holds for the whole set. In short, we need this feature of a set to know that it has this onto function from the natural numbers for proof by induction to be valid, and this whole machinery just seems a little much for where we are located at this point in the development in the text. So I'm just a little suspicious of doing proofs by induction up to this point. I'm sure eventually, especially when we maybe have results about one-to-one functions and onto functions and things like that, maybe later on I will feel more willing to do a proof by induction, but at least for the time being I'm suspicious of it. So I am going to attempt to do this not by induction. Now, if I'm going to do it not by induction, then what I might observe is that if x doesn't have 0 and it doesn't have 1 and it doesn't have 2, then it sure looks like the complement of x is an inductive set, and I would like to be able to prove that. If I could prove that, I feel fairly good that I could derive some sort of a contradiction somehow. So that is going to be how I attempt the proof here. Okay, so let's go ahead, state the assumptions, define this set y to be the complement in n, the complement of x in n, and I would like to argue that y is an inductive set. Well, I think that the empty set is in y trivially. Now, to me, the more substantial part is showing that if anything is in y, then it plus 1 is in y. Well, suppose for contradiction that it's not in y. Okay, not being in y entails that it is in x. I mean, I'm taking my universe here to be n, so I could state things a little more rigorously, but you know what I mean. And since a plus 1 is in x, but by assumption from back up here, a is not in x, so I claim that it should come out that a plus 1 is in min, in x. How do I show that a plus 1 is in min? Well, I need to show that if anything is in a plus 1, it is not in x. How am I going to do that? I take an arbitrary element out of a plus 1. Of course, as always, this implies that either b is in a or b is equal to a. Now, the left branch of this is very hard. I would like to show that b cannot be in x, but how am I going to get that? I would, need some reason for thinking that a is a subset of the complement of x or something like that. And it doesn't seem readily available. Whereas the right-hand branch is quite trivial, since we know that b is equal to a on the right-hand branch here, and we know that a is in y, and therefore a is not in x. That branch would be really easy, and I interpret the reason for this split in the difficulty along these two branches is that this is more or less just considering the previous case, right? The case previous to A, and we have access to it immediately from all of our assumptions. But being in A is considering all of the cases that are less than A, and that's really hard to do. I mean, it should come out true, but the assumptions of our proof don't make it particularly easy to think and talk about that. So I could struggle really hard to make the proof work, but I think it would be easier if I had just defined y in such a way as to incorporate features I know that it has, namely that it's accumulating all of these elements as it goes, and I don't always have to talk in terms of a given element and the one that came previous to it, if such exists, and so on. So I claim that this proof will become a lot easier if I select a set y so that everything, everything less than it is immediately sort of grouped into y, and I, in some sense, have access to it. That would just be the things that do not intersect x, right? The numbers that do not intersect x, if those are, the components of y, then I would have that a is a subset of the complement of x. And also the set of, as I'm going along collecting things that are not in x, the fact that they do not intersect x is also just kind of reflective of the fact that they're in the complement. So that's my strategy, and so in the next video I will actually pursue that.